In this video lesson, we're going to be looking at how to apply the sine law and the cosine law given different situations where it doesn't tell us to use the sine law or the cosine law. So really quick recap, sine law, the equation to represent the sine laws looks like this: sine of angle A over length A, sine B over length B, sine angle C over side length C. And you can only use the sine law when you're given two angles and a side, or two sides and a non-contained angle. The cosine law is represented as c squared equals a squared plus b squared minus 2ab cos of angle C. And you can generally solve for the side length given this equation, or you can rearrange to solve for the angle. You can use the cosine law when you have all three side lengths, s, or two sides and a contained angle, so the angles between the two sides. Let's do a couple examples before we jump into the word problems. Example number 1 tells us to determine whether we should use the sine law or the cosine law to solve for the indicated side or angle measure. Then to solve the triangle, and round any side lengths to one decimal place and any angle measures to the nearest degree. Looking at letter A, we have a side length, and an angle. So it follows SSA. That corresponds with the law of sines. So in order to solve for my triangle, I'm just going to give some arbitrary vertice labels to my triangle, so x, y, and z, and I'm going to set up my sine law in terms of x, y, and z. So from here, I can take the variables that I know and I'll plug them into my sine law equation that I just set up. So I know nothing about the x variables. So in order to solve for my x variables, I first need to solve for, let's say, my y variable. So I'm going to go ahead and use this side of the sine law equation, and I'm going to solve for my y angle first. So to do that, I'm just going to rearrange my equation, isolate for y by using sine inverse of whatever I got in my calculator, so 0.453, and I get a y angle of 27 degrees. From there, it's as easy as using the sum of interior angles theorem for the angle x to solve for angle x. So we get an angle x of 138 degrees. Then we can apply this angle x into our sine law equation, and that would tell us that we only have one variable to solve for, so we can go ahead and solve for that variable, and we get an x value of 20.7 centimeters. So you're probably wondering, hey miss, this x angle looks way too big to be in this diagram. Yes, it does look way too big, but you also have to keep in mind that not every single diagram is going to be exactly to scale. So some of them will throw you off, but as long as your algebra is correct, then you're doing it properly. So I've just highlighted the three main answers that will solve the triangle. Pause the video here and see if you can solve for B by yourself. When you come back, you'll notice it follows side, angle, side, so that fits into the cosine law. We're going to give arbitrary variables to those vertices and then plug them into the cosine law. X squared is equal to y squared plus z squared minus 2yz cos of x. So in this case, we're solving for the x side length first. You can plug in your numbers to your cosine law equation and solve for x. Don't forget to square root, and you get an x side length value of 49.3 millimeters. Then you can go ahead and solve for one of your angles. In this case, I chose to solve for angle y using the cosine law. So we've rearranged the cosine law in order to isolate for that angle y. We use cos inverse, and we get an angle of 43 degrees. To solve for z, it's pretty simple. You can apply that sum of interior angle theorem, and our angle z happens to be 62 degrees. So if you want to just highlight those final answers, these are the main answers that will solve the entire triangle for you. Letter C. Again, pause the video and try letter C and D by yourself and come back and see if you've got them right. So letter C, I've labeled P, Q, and O for the side lengths, and I know since I have all three sides, I'm going to use that cosine law in order to solve for my angle theta. So solving for angle theta, cos theta is equal to O squared minus P squared minus Q squared over negative 2pq, and I just plug in my values for each of the corresponding variables, and I can go ahead and use my inverse cos to solve for my theta. I get a theta of 72 degrees. From here, I can find another angle. So in this case, let's solve for angle Q. You could have solved for angle P as well, but I just solved for angle Q. Cos of Q, set it up, and plug in your variables to solve for your angle Q. You get an angle Q of 49 degrees. From here, it's pretty simple. You can use that sum of interior angles theorem to solve for angle P. And those are your final values in order to solve for that triangle. In letter D, it follows the angle side rule. So we've got two angles and one side. So we're going to follow the sine law. Give those vertices and side lengths arbitrary variables. And the first thing that I notice that I can solve for is my theta. Pretty simply, we can use that sum of interior angles rule to solve for theta, and it gives us 76 degrees. From there, I'm going to set up my sine law. A over sine of 13 degrees is equal to B over sine of 91 equals 6 over sine 76. Now I'm going to solve for my B value. You could have solved for your A value first, but I'm just going to go ahead and solve for B. So I isolate for B and I get 6.2 centimeters. Then I'm going to solve for my A value. A over sine 13 equals 6 over sine 76. Isolate for my A value and I get an A value of 1.4 centimeters. So again, I'm just going to highlight my final answers, and those are the answers that will solve my triangle. Let's jump into the word problems now. Number 2, an architect designs a house that is 12 meters wide. So I'm just going to draw a house, label it 12 meters wide so far, and if I know the bottom is 12 meters wide, then I know the roof, just below the roof, whatever's holding up the roof is 12 meters wide as well. So the rafters holding up the roof are equal in length and they meet at an angle of 70 degrees. So I'm going to label them both R because they're the same value, and they meet at an angle at the top of 70 degrees. Now, there's something else that we know. The rafters extend 0.3 meters beyond the supporting walls. So I labeled that. We need to find how long the rafters are to the nearest tenth of a meter. So because the rafters are the exact same length, my first thing that I know is that I've got two angles here that are the same because it follows an isosceles triangle. Two sides are the same, so two angles are the same. Now, in order to solve for the rafter length, I need to solve for my R value first and then add 0.3 meters to it. But because I only have 12 meters one side and 70 degrees one angle, I can't really do much until I find two other angles or two other pieces of information. So I'm going to find those two angles by applying the sum of interior angles rule and solving for my theta to give me 55 degrees for each of those angles. Now I have two angles and one side, so side angle follows the sine law, and I'm going to write out my sine equation here that I can use, my sine law equation. So my R value divided by sine of theta is equal to 12 divided by sine 70 degrees. From here, I can plug in my theta and isolate for my R value to give me 10.5 meters. That's the length of the R value, but it's not the full length of the rafter because remember that rafter extends out 0.3 meters. So we're going to have to add 0.3 meters to it to give us 10.8 meters. So therefore, the rafters are 10.8 meters long. Number 3. A chandelier is suspended from a ceiling by two chains. One chain is 46 centimeters long and it forms an angle of 60 degrees with the ceiling. The other chain is 65 centimeters long, and we don't know what angle it forms with the ceiling, so we need to find that. Now, before I came across this little diagram, I went through a few other diagrams. So solving these word problems is all about getting the diagram correct. Whatever diagram makes the most sense, that's the one that will most likely give you the right answer. So it's all about your diagrams. So with this diagram, I know that I've got two sides and one angle, so side angle follows my sine law. I'm going to apply my sine law, sine theta over 46 equals sine 60 over 65, and I set it up in terms of theta so that I can solve for theta pretty easily using algebra. I use my inverse sine to give me my theta value of 38 degrees. So therefore, the longer chain makes a 38-degree angle with the ceiling. In number 4, two tracking stations 20 kilometers apart measure the angles of elevation of a rocket that was launched with a weather satellite. From station A, let's draw station A, From station A, the angle of elevation is 41 degrees. So these stations are recording how high the rocket goes. The angle of elevation to station A happens to be 41 degrees. So you can see here I've drawn the path of the rocket and the station A, which measures the rocket at an angle of elevation of 41 degrees. From station B, there's station B, The angle of elevation is 75 degrees. We know that the two stations are 20 kilometers apart. So what is the altitude of the rocket given that information? So we need to find the altitude, and we'll call that h, height. So in order to approach this question, I'm going to look at these two triangles as two separate entities. So let's look at the first triangle on the left-hand side because it gives us the most information. So we've got this triangle. It has an angle of 41 degrees and one side length of 20 kilometers. But there's something else that we know about it. We can use that the supplementary angle theorem to solve for the angle right here. So to solve for that angle, 180 degrees minus 75 equals 105 degrees. So if we know that is 105 degrees, we have two angles and one side. So side, angle follows the sine law. In order to set up our sine law appropriately, we do also need to solve for the angle right at the top. So let's call that theta, and to solve for that, we can use the sum of interior angle theorem, and we can get 34 degrees for that theta. Okay, so from here, I labeled this side A just to set up my sine law appropriately. So I've got side length A divided by sine of 41 degrees equals 20, which is what we know, divided by the sine of theta, or the sine of 34. I can go ahead, rearrange my equation, and isolate for A, and my A value happens to be 23.5 kilometers. So if this side length is 23.5 kilometers, then I can look at my right-hand triangle, which doesn't have a lot of information until now. So now, looking at my right-hand triangle, that hypotenuse value is 23.5 kilometers, and we know two angles in that. One is 90 degrees and one is 75 degrees. So again, we have a side, an angle, and an angle, so it follows the sine law. So we're going to set up the sine law for the green triangle. And just for more organization, we'll label that side a green triangle and that side the blue triangle. So setting up my sine law for the green triangle, the triangle on the right-hand side, we're going to do h over sine 75 is equal to 23.5 over sine 90. You can go ahead and isolate for h, and your h value happens to be 22.7 kilometers. So therefore, the rocket's altitude is 22.7 kilometers. Number 5 is a fun example. So we've got two roads and they diverge at a 46-degree angle. Two bikers, so I drew little bikers at the bottom just to help you understand a little bit more. They take separate routes at 15 kilometers per hour. So I've labeled this guy biker A, he travels at 15 kilometers per hour, and biker B travels at 20 kilometers per hour. How far apart are they after 1.5 hours to the nearest kilometer? So we need to find the distance between these two guys to the nearest kilometer. So how do we do that? Well, first, let's look at each individual biker's path. So we're going to look at the purple biker's path first. So biker A, and we know that he travels at 15 kilometers per hour. But they're traveling at an hour and a half. They're traveling for an hour and a half. So we need to determine how many kilometers this guy traveled in an hour and a half. In 1 hour, he travels 15 kilometers. So it only makes sense that in 1.5 hours or 1.5 hours, he can travel 22.5 kilometers. So we can do that simple equation just by using a ratio d, distance over time. So we know that he travels 15 kilometers in 1 hour. So how much does he travel in 1.5 hours? We can go ahead, use cross multiplication to solve for that, and we get 22.5 kilometers. So we know the distance that this guy travels is 22.5 kilometers. Let's do the exact same thing for biker B, the blue path. We know biker B travels 20 kilometers per hour. We're going to apply that same ratio in order to solve for the distance that he travels in 1.5 hours. So he travels at 20 kilometers per hour, so in 1.5 hours, he travels 30 kilometers. Knowing this, we now have two sides and one angle. So we can apply that cosine law, side angle side. So let's set up our cosine law in terms of solving for side length C. So side length C is just across from angle C. And we can do that and plug in our values for our cosine law. and solve for our C length value by square rooting both sides to give us 21.6 kilometers. So therefore, the bikers are 21.6 kilometers apart. Here are some more practice questions.